Hello friends, now I am going to talk about boundary conditions, probability current density and applications of Schrodinger equation for particle in 1 and 3 dimensional box. Now, Bond's interpretation of wave function is rho equals to psi star psi, and this is probability density, and rho dx is probability of finding the particle between positions x and x plus dx. It is a very fundamental postulate and it gives you the physical significance of wave function psi. So, psi star psi dx is the probability. Now, if I integrate rho dx between the limits a and b, this would give me probability of finding the particle between a and b at time t. And now, if I let a goes to minus infinity and b goes to plus infinity, then this integral minus infinity to plus infinity rho dx is probability of finding the particle between x is equal to minus infinity and x is equal to plus infinity at the time t. And this must be equal to 1, because we know that the particle is certain to be found somewhere between minus infinity and plus infinity, and the corresponding probability is 1. So, because of this certainty, this integral is 1, and the wave function satisfying above conditions are called normalized wave functions. Then we talk of square well potentials. Our goal is to describe behavior of particle moving in certain potential V x, that means V depending on x. To keep the mathematics simple, square well potential models are used to represent real potentials. Now, square well potentials remain constant in certain range and jump suddenly to some other values and remain constant again in certain ranges. This is given by these diagrams. You can see very well that V is changing with time, but there is an interval in which the V remains same and then suddenly it changes its value, then again for some interval it remains same. These kind of potentials are called square well potentials. Now, I must tell you that real potentials could be different, but for mathematical simplicity we are considering these potentials. Then the boundary conditions. Now, the Bond's interpretation of wave function puts following conditions on psi x t. First, it should be continuous everywhere. For any point x 0, the left hand limit, that is psi x 0 minus e limit epsilon tends to 0, must be equal to psi x 0 plus epsilon tends to 0. That is, the left hand limit and the right hand limit at the point x is equal to x naught must be same. That is the continuity of the wave function, and the failure of this condition would lead to two different values of probability density psi star psi at any point x 0, which is unphysical, because at any point x 0 we cannot have two probability density or two values of the probability. Then the wave function psi x t should be finite at all points in space. Failure of this would make probability more than 1. Then psi x t should be square integrable so that the probability is well defined. Then we note some more conditions on psi and its d psi by dx, that is the differential of psi, and this is obtained by integration of time independent Schrodinger equation, and this integration as you note here gives you the relation minus h bar square by 2 m del phi by del x evaluated at x 0 plus epsilon minus del phi by del x evaluated at x 0, and then this is equal to the integral that you note here e minus v x phi x dx, and epsilon I have told you is a very small quantity. That means, you are integrating the differential equation between x 0 and x 0 plus epsilon. Then you can see very well from this equation that the continuity of del phi by del x, that is the differential of phi, is assured if potential V x is continuous, and even if the discontinuity of V is finite. But if the discontinuity of V is infinite, then del x phi is not continuous. So, what we are trying to see, that under what conditions the differential of phi is continuous or not continuous, and the difference is that the V should not be infinite. If V is infinite, then del phi by del x is not continuous, otherwise it is continuous. Then come to the probability current density. Consider motion of a particle in one dimension along x direction, and let A be some area perpendicular to x direction. That is what we consider the situation like, and then psi star psi dx is the probability of finding the particle between x and x plus dx in the volume A times dx. This is very obvious, we consider the volume and then we consider the probability. Then with time psi x t changes, and so does this probability, but the probability is a conserved quantity. If it decreases in one region, it should increase in the nearby region. It is analogous to the fluid flow. We may think that the probability flows in and out of this volume and is governed by probability current density vector j, whose x component is j x. Then the net probability flow per unit time out of this volume is del x j x into a dx, and from the conservation of probability, this must be equal to the rate of decrease of probability in the volume a dx, and it is minus d rho by dt times a dx. And this simple consideration leads us to continuity equation in one dimension, that is del x of j x is minus del t of rho minus del t of psi star psi. Now, we have also Schrodinger equation, which is given by d psi by dt, and then if we just use these equations and its complex conjugate, it is easy to show that del x of j x satisfies the second equation that you see on the slide, and then you define a term j x, which is h bar upon 2 I m psi star del x psi minus psi del x psi star, and this represents probability current density in one dimension. The idea is that by considering certain volume and by considering the fact that the probability is a conserved quantity, you come across a vector which is called the probability current density, analogous to the flow of the fluid. Now, what is the probability current density for a free particle travelling in along the x direction? As I told you, for a free particle, the wave function is given by psi is equal to a exponential of I p x minus e t by h bar, and with this psi and the relation for j x, which you see on the second equation, you immediately get j x as p by m psi star psi. Now, compare this with j x is equal to rho v for the fluid moving along the x direction, and you note that fluid velocity v goes over to p by m, which is the particle velocity, and the fluid density rho goes over to psi star psi, which is the probability density. Now, we consider the problem of particle in one dimensional box. What exactly is one dimensional box? One dimensional box is the situation where you have confined a particle of between a region of length L, and for x is less than 0, the potential is infinite. Between x is equal to 0 and L, it is 0, and when x is more than L, it is again infinite. So, the particle finds itself in a one dimensional box of length L and cannot move out of it unless it requires infinite energy. Another name of this potential is infinite square well potential. So, you can say either it is a particle in a one dimensional box problem or it is an infinite square well potential. It is the same thing. This is the diagram corresponding to the particle in a one dimensional box of length L. You note here that the particle cannot move out of the region unless it has infinite energy to overcome the potential. Because it cannot have infinite energy, it will always remain in the box. Hamiltonian operator in the region x greater than 0 less than L is h is equal to p square by 2m operator, and is minus h bar square by 2m del 2 del x 2, because v term, that is the potential, is 0. Now, the energy eigenvalues are obtained by solving time independent Schrodinger equation minus h bar square by 2m del 2 del x 2 phi is equal to E phi, and this is in the form d2 dx 2 phi plus k square phi is equal to 0, where k is square root of 2 m e by h bar square. Now, note here that the partial derivative del del x and the total derivative d dx are same in one dimension. They are different in more than one dimension because there is no y and z term. So, we need not distinguish between the total derivative and the partial derivative. Equation for phi is the same as that for simple harmonic oscillator, and we know that the solution of simple harmonic oscillator is a sin k x plus theta. So, we have phi is a sin k x plus theta and x is greater than 0 and less than L. Now, phi x is equal to 0 when x is less than 0 and x is more than L, because infinite barrier prevents the particle from reaching this region, making the probability density 0. This is very important to note, that why we put phi is equal to 0 when x is less than 0 and when x is more than L, because the particle cannot be there. If it cannot be there, then psi star psi should be 0, that means psi should be 0. So, the phi or the wave function is 0 in this region. Then we have the boundary conditions at x is equal to 0 and which is a sin theta is 0. So, either a is 0 or theta is 0, but a is 0 makes phi is equal to 0 everywhere and corresponds to the trivial solution. Hence, theta is equal to 0 and that makes the solution phi is equal to a sin k x when x is more than 0 and less than L. You see, we have used a fact that the trivial solution should be excluded, and that is excluded by making a not equal to 0 and theta is equal to 0. Then we have another boundary condition at x is equal to L. When x is equal to L, phi is equal to a sin k L, and this leads to k L is equal to n pi, where n is 1, 2, 3. Now, here again we note that n cannot be made equal to 0, because if you make n is equal to 0, then k would be 0, and when k is 0, then phi is 0 everywhere, that is again a trivial solution. So, we do not want a trivial solution but we need non-trivial solution. So, for the non-trivial solutions, KL must be equal to n pi. Then the negative values of n need not be considered, because that will just make phi goes to minus phi, and that will not be a different state. So, k can take only certain allowed values, which is k is equal to root of 2 m e by h bar square is equal to n pi by L, and n is equal to 1, 2, 3 etcetera, which are the integers. It means that not all values are allowed for E, and it can take only these values, which are E n is n square pi square h bar square upon 2 m L square, and n is 1, 2, 3. These are the quantized values of energy. No other energy values are possible. The ground state energy, this is the lowest possible energy and corresponds to n is equal to 1, and E 1 is pi square h bar square upon 2 m L square. And for the excited states energy, n is not equal to 1, and these are called the excited states energy, and you note that E n is n square times E 1, and you also note that the energy values are quantized. Quantized means they take only certain energy values, which are given by these expressions, and not all continuous values of energies. Now, in classical physics, ground state energy is 0. In quantum physics, ground state energy is E1, and it is not equal to 0. How it is explained in quantum physics? And one way is that by invoking the uncertainty principle. We note that the particle is restricted to the region L. So, the maximum uncertainty delta x must be equal to less than L, because after all it is always in the region, and it cannot go out of the region. And then if you use the uncertainty principle, then delta p must be more than h bar by 2 L. Now, here it is delta p. What about the actual p? So, actual p should at least be of the order of the delta p uncertainty. So, we can estimate that the p minimum should be of the order of h bar by 2 L. Once we have an estimate for p minimum, then the energy minimum is decided by p minimum square upon 2 m, and it comes out of the order of h bar square upon 2 m L square. That is what we saw in this expression also. So, we can convince ourselves that the minimum energy not being 0 is consistent with the uncertainty principle, and it is not quite understandable from the classical physics, because in the classical physics regime we should expect the ground state energy to be 0, because the lowest kinetic energy is 0 in the region. Here we see the wave functions and the probability current density and allowed energies for n is equal to 1, 2 and 3, and you see that the energy is quantized. Here we write the energy eigenfunctions, which are phi n x, and this is sin n pi by x times L multiplied by ANs are constants, and then you have the normalized conditions, and then that puts the value of AN as root 2 over L, because after all the integral should be equal to 1 corresponding to the normalized wave functions. So, we have the normalized wave functions phi n x is root 2 by L sin n pi x over L when x is more than 0 and less than L, and it is n is 1, 2, 3, and the phi is 0 otherwise. When x is outside this region, then phi is 0. Then the general solution of this equation is psi is sigma Cn phi n, where Cn's are constant, and this evolves with time according to this equation Cn phi n exponential of minus E n t by h bar. This is the general solution of the wave function. For n is equal to 1, the particle has the maximum probability density to be found at x is equal to L by 2. For n is equal to 2, the particle cannot be found at x is equal to L by 2, because mod phi 2 square vanishes there. D phi by dx is discontinuous at x is equal to 0 and L, because I told you that d phi by dx is going to be discontinuous if the v is infinite. We do have v infinite here. So, d phi by dx is discontinuous at x is equal to 0 and at x is equal to L. This is the case for computing x averages and p averages for phi and x. It is easy to compute these integrals, and one can show that x average is L by 2 and p average is equal to 0, which is what you expect by looking at the curves. Now, we go over to another case, which is particle in 3-dimensional box. The difference between one particle and the 3-particle box, 1 dimension and 3-dimensional box, is that now you have this binding, the trapping from all the sides. Previously, we had trapped only in the x direction. Here, v is equal to 0 for x greater than 0 less than L, y greater than 0 less than L, z greater than 0 less than L, and is equal to infinity otherwise. So, that means we have trapped the potential from all sides, from in x, y and z directions. Clearly, psi is non-zero only in the cube of this length, and the Schrodinger equation is now del 2 del x 2 plus del 2 del y 2 plus del z 2 on psi plus 2 m e by h bar square psi is equal to 0. This is the Schrodinger equation for the 3-dimensional box problem. Then we can use the method of separation of variable. We are saying that psi, which depends on x, y and z, is a product of 3 functions capital X, capital Y, capital Z, each depending on x, y and z only. It is a simple matter to show that the first term depend on x alone, second on y alone and so on. Then the capital X should satisfy certain differential equation, which is given by 1 over capital X d2 dx to capital X is equal to minus kx square x, and similar for y and z. Moreover, the sum of the squares of kx square, ky square, kz square is given by 2 m e by h bar square. Then now we have to impose certain boundary conditions on these as we did before. Now, the solution for x must be of the form x is equal to a sin kx x plus b cos kx x, and because at x is equal to 0 and x is equal to capital L, this must vanish. So, we must have b is equal to 0 and kxl is equal to nx times pi, where nx is equal to 1, 2, 3 etc., as we had in the case of 1-dimensional box, and similar arguments apply in y and z directions. So, we have the possible energies of the particle E as pi square h bar square upon 2 m L square multiplied by nx square plus ny square plus nz square, and each of nx, ny, nz are integers now ranging from 1 to infinity. And here are the corresponding wave functions. They are similar to the wave functions in the 1-dimensional box, and then the difference between the 1-dimensional box and the 3-dimensional box is the degeneracy of the states. A set of integers nx, ny, nz specifies one particular state of a particle in 3-dimensional box with energy E is equal to pi square h bar square upon 2 ml square n x square plus n y square plus n z square. If there exist n different sets of integers n x, n y, n z giving same value of E, then this state is said to be n-fold degenerate. It means for the same E, we should have more than one psi. If this is the situation, then it is a degenerate situation. For example, state of a particle in 3-dimensional box with energy E is pi square h bar square upon 2 ml square is 3-fold degenerate, because for 3 different states 1 0 0, 0 1 0, 0 0 1 E remains the same. This is the idea of the degenerate case. So, in the 3-dimensional box we have a degeneracy which is not there in the 1-dimensional box. What we have seen today is that the Schrodinger equation, when applied to 1-dimensional and 3-dimensional box, yields results which are not expected from classical physics. The energy is quantized. This is the message which we get from the quantum physics, and this is we get by simple applying Schrodinger equation and subjecting them to certain boundary conditions. Hope you have enjoyed this lecture. Thank you.